Good morning, student. I welcome you again in this morning session of molecular reaction dynamics. And I have already discussed regarding the important features of molecular reaction dynamics. I have also discussed the elementary idea about the femtosecond spectroscopy. Today, I am going to discuss the last part of your course content, that is direct probing of the transition state. And if time permits, I will also discuss the elementary idea about the barrier-less chemical reactions. Barrier-less chemical reactions. Now, as you know that whenever I do start any type of topic, I always share some of the recent and old references related to that subject, because transition state is not a new terminology. You all are aware of this transition state from your, I think, from your B.Sc classes or even in school days. But the question is that how do you probe that transition state? That is the objective of this short lecture. Now, many times I have shown you this, my most favorite book, and today's presentation is completely based on this book. Of course, it is an edited book and there are many chapters edited by a great scientist of our country, Professor N. Satyamurthy, and the title of that edited book is Reaction Dynamics Recent Advances. So even barrier-less chemical reaction is also available in this edited book. But today I am concentrating only on direct probing of the transition state, and fortunately that chapter is written by Professor Satyamurthy. So I can give this book to you for your reference and other things. And particularly in this chapter, he has given the most of the information published by a Nobel laureate, Professor Polanyi. So because the direct probing of the transition state, the credit goes to Professor Polanyi. And the fundamental point is very simple. If we are talking about any type of reactions, and everywhere they are given these reactions. Many times I have written to you A plus BC. Many times I have written this type of reactions, and I will explain that what is actually transition state. The reactant product, but we are concerned about this transition state, which is supposed to be right A, B, C. You can write like that also. Very, very common thing. But mostly there are many methods available for probing of the direct, I am talking about the direct probing of the transition state. But today I will explain only one method. And the method is based on, very simple, to monitor the absorption or emission of the product. That's all. That is the objective of today's presentation. Similarly, as you know that because I always advocated the research-oriented teaching, you must refer some of the excellent research articles related to that subject. So again, I am talking about this transition state, and there is an excellent, I must say, it is one of the best review article written by a great scientist, Professor Brooks, because chemical review, you know, it is one of the high impact factor journals of our published by the American Chemical Society, and here everything is there, that what is the scope and the activation of the chemical reactions, emission and absorption, as I told you. That our objective is that how to probe that type of transition state. And again, there are two methods, absorption or I am not talking about the femtosecond spectroscopy and other things. So this is available in our library also, so you must refer this chemical review so that you can understand the time scale of this type of the chemical reactions and other things. And in this particular presentation, I will take some of the simple reactions, like reaction between the potassium and sodium chloride, reaction between the potassium plus HgBr2, like that. So again, I have also read this paper, and this is also very good paper. Again, it is written by some Harland and Burns, and it is also very good journal, again American Institute of Physics, Journal of Chemical Physics, structure of the transition state. Structure of the transition state, which is very important, that how, of course there is a collision, you all know that, but the observation of transition region species is very important. Similarly, you are all aware of, because I have already discussed because this is in your course, that is called the femtosecond spectroscopy, or sometimes it is called the transition state spectroscopy. Today I am not going to discuss the transition state spectroscopy, but without the reference of Ahmed's well, this lecture will be incomplete, because that is, of course, is in your course, that is under the femtosecond spectroscopy, and it is also published in Faraday discussion. It is a more modern method, transition state theory, but femtosecond 10 to the power minus 12, 10 to the power minus 15, like that. So today I will not discuss the femtosecond spectroscopy. Now, last and most important research paper, and you must refer this paper, because this is a unique paper. Why it is a unique paper? Because this paper was written by two Nobel laureates. So it is a very unique paper. One Nobel laureate, you all know that, Professor Polanyi, 1986. So, and another, 1999. Although this paper is published in 1995, he was awarded Nobel Prize in 1999. But this paper was written 1995. But this is the exact what I am going to present you, direct observation of the transition state. So you follow my point. This is the most suitable paper published in the American, again this is of course American Chemical Society journals, account of chemical research, very good. Again, everywhere you are going to see the same thing, A plus B and AC. Everything is exactly same. Interatomic distance, potential energy, everything is there. So interatomic distance of this BC, interatomic distance of the AB, interatomic distance of AC, like that, with that potential energy. But why I just want to show you these things, the definition of transition state. You will be happy to read this definition of, from school level you are studying, activated energy, like activated complex, like that. Okay, just you read it. See the language of these great Nobel laureates. The full family of configuration. You follow this point. Full family of configuration through which the reacting species evolve en route from reactants to product. So direct probing means we have to catch the absorption and emission spectrum of that type of product. Sometimes what happened, we have to use some laser beam also to just complete that type of the reactions. But ultimate objective is that we will figure out that absorption and emission spectrum of that type of species. So now I can start the things. Now, so there are many methods. Resonance is also one method. Transition state spectroscopy is also another method, that is called the femtosecond. That is femtosecond. That is also in your course. I have already. Ab initio quantum mechanical method is, of course, it is a computer based method. It is not required for the student. And I have also taught the infrared chemoluminescence method. I remember, that is IRCL method. IRCL method. Infrared chemoluminescence method. Reaction between HI and Cl. I just remember this thing. But now, today, again and again I am saying same thing, that our today's objective is that direct probing of the transition state. Let me start. Now, first point is that whatever I am going to teach you, that is based on the research paper of Polanyi. So therefore, you can call it, it is one type of Polanyi's method, because I have referred the two important research paper. So where what they are doing, they are studying a very simple reaction between fluorine and sodium, and monitor the sodium. You all know that sodium sometimes emitted some light. So by monitoring that sodium emission, they are able to calculate the transition state. How? Now again I am just writing this thing. You can write like that. F is react with This is the first method developed by the Polanyi. So it is first it is converted into activated state. You can write FNANA or NANAF like that. So this is activated state. Then it is converted into NANAF. Excited state. Now there are 2 stars like that. Then, now the most important part, it will give the NAF plus NA star, which is very important. And that Na star is giving the sodium D line emission. And this D line emission is corresponding to the energy difference. That means if we plot a graph between the potential energy and angle between these two things, so we can determine the transition state directly. And that was, of course, there are some problems, so they modified that equation, but this is the first method by which you can. Now I will show you the graph for this method. Now, if before I plot a graph between the potential energy of that different d wings in terms of electron volt. Okay, I'm just imaginary. It can be 1, 2, 3, 4 like that. Just take one. And one theta. I'll tell what is theta, degree centigrade. And it is again, suppose I am taking the first theta angle is 12.7 degrees. Second is 25.4. $38.1, that is approximately 50.8. You follow my point? Now you have to understand that what is theta and what is potential energy. For that, I am taking you another example. The reaction between helium and hydrogen. Of course, this is like that. Again, I am writing helium plus H2, HEH plus, just suppose, plus H. So same type of the reactions. Now there are more than 3 coordinates. One is this, the distance between interatomic distance, this, another is this, another the potential energy. So if I Suppose this is He H2 plus and here is He H plus. So suppose this type of thing. You know about the coordinates and other things. Now this angle is theta. And this is rho. So such type of, there are three types of coordinates, and you might have heard about the spherical coordinate, theta, phi and other thing. So some elementary mathematics is required for that. That is called hyperspherical coordinate system. And there are, if you want to learn about this hyperspherical coordinate for the chemical reaction dynamics, because today's my objective is only to probe the direct transition state. So I am not going to discuss about what is spherical coordinate and what is hyperspherical coordinates, but you can understand by this simple method. I am just giving one example. So there are so many problems are there, we can like that, but just so for change in theta and different types of this coordinate. So one coordinate is fixed. So we vary the potential energy and that theta at different type of this another type of the coordinate. So that is called the hyperspherical coordinate for the chemical reaction dynamics. And it is also published in Advance in the Quantum Mechanics and Quantum Chemistry. So don't worry about this complicated mathematics. You just see such type of things. So let me erase these things. So these are all D-line emission. D-line emission. Okay, I can change the color also. Green. So first case, suppose what is our objective? To monitor the potential energy of that emitted D line with respect to this theta angle. Angle may be 12.7, 25.4, 38.1, 50.8 like that. So first case, suppose the rho value is very high, around 9 approximately. I can count 7, 6 and 4. So it's a hyperspherical coordinate. So what I am getting, I'll get such type of so it is a D wings corresponding to the D line wings. It is normal potential energy. Suppose this is for 7. Blue. Slightly different. Maybe 6. Maybe 4. Black. Like that. So it may be 4. So what does it mean? That emission of this D line comes from the isolated sodium, and all such type of D lines are related to the energy difference between the reactants and the product. So the conclusion is that the different wings, these are called the different wings. These are called different wings of that sodium D line. So that different D lines can give the information about the energy spacing between the two states. So one could infer the potential energy surface and the fast type of the reaction. Why I am talking about the barrier-less chemical reaction? These are very fast reactions, and lifetime is, you can understand, 10 to the power minus 12 seconds, less than the sodium, and by that method one can monitor the transition state. But there are some problems. So that method was developed by the Polanyi. So then another scientist, his name is, of course, Polanyi is also there, but the other scientists, Smith and Stolo, they slightly modified that method. So in place of sodium and fluorine, sodium chloride, they have taken deuterated things. So the new system is, just see here. So what is new system is, they have taken the hydrogen and react with D. So now how we get that hydrogen? So we need some generator to produce that hydrogen. So they are taking a H2S gas. So now actually Polanyi initiated some instrumentation technique. So there must be sometimes it is called the 3-beam type of the experiment. Why 3-beam type of the experiment? Because in one side H2S gas must be pumped through a laser, so it will give the hydrogen. Another beam, there is D2, and then photon and other things. So that is sometimes called the beam type of the experiment. So first laser is L1 laser, pump the H2S gas to generate hydrogen, which react with the D2. And while I was studying with you the femtosecond spectroscopy, I discussed pump probe laser. Have you remembered this pump probe laser? Pump that is excited into then there is a reaction, and then we apply the another type of probe to monitor that system. So by same type of the things, the first laser for the generation of the hydrogen through H2S gas, second it reacts with the D2, and then this transition state is formed, and with the help of second laser, that transition state can directly be detected. Only thing, we have to monitor this lifetime of L1 and L2. So that was also proposed by the Polanyi, but it is slightly modified method. So first method, always remember the first method is very simple method, this type of the reaction, sodium and fluorine reaction, and second method is slight modification by the Polanyi, but to and different. The last method, that is also proposed by other scientists. Although I told you that in 1986 there is a Nobel Prize of Polanyi, Herzberg and Lee, and they have studied the molecular reaction dynamics first time using the infrared chemoluminescence method and crossed molecular beam method. So here is also, because here is three things. So therefore, it is sometimes it is called the three crossed beam of the experiment. And again, here is also same thing, that we have to monitor the fluorescence of that product. Okay, so let me explain the first method. First method, what we have taken? They have taken the potassium first. Very simple and easy to remember also. 3 beam, one for potassium, second is the AgBr2. First, they form a transition state. Then again we apply photon, so it will form KAgBr2. Now this is activated. Now this will give the KBr and AgBr2. This AgBr2 gives the fluorescence. So by monitoring this fluorescence, you can probe the transition state. That method was proposed by P.R. Brooks. I have already shown you that the review article of that Brooks. Is a great scientist of the physical organic chemistry. Then there is a slight modification. Why it is called the cross beam? One side is this. I am not going to discuss the instrumental method of cross beam molecular method, but this is also in your course. You must read the experimental method of infrared chemoluminescence method as well as molecular beam experiment. There is a possibility of short question. What is the importance of molecular beam experiment and infrared chemoluminescence method? It is also a possibility of the short type, because how transition state can be directly probed. Then of course you have to write, and you are experiencing that I am using the simplest method. I am not using any complicated mathematics or anything. I am just using very simple method, and I have taken all the example from that book of Satyamurthy. Okay. Now the last example. Then we will come to that barrierless chemical agent. Now in place of AgBr2, they have taken K plus NaCl. Same procedure is exactly same. Formation of KNaCl, or you can write KClNa also. You can write, so absolutely no problem. Same thing. It is easy to cram, easy to understand. No complicated mathematics is there. So again it forms KNaCl or KClNa. You can write also. Absolutely no problem. If you write KClNa, I don't mind. Then it is converted into KCl, and again that Na, just writing green color, because sodium emission is very easy to monitor. So this is called the crossed beam experiment. 3 beams. Why 3 beams? Because everywhere you need this and this, and this photon is the laser type of thing in that spectroscopy. So now again this last part. So it is a general general observation that it is called, in one sentence I can call it a transition state emission. What is called transition state emission. It is called transition state emission. So if I plot a graph between the energy, again energy, and of course product separation. This is the last product separation. Can I change the color? Like that. Here is, you can call it is this is the actual transition state. And here is starting point, this AB plus C is a product. C star because C star is I'm giving like that. Okay. So then there are different. Now you just remember the first sentence. You remember the first sentence. Full family of configuration through which the reacting species en route. You are coming from Delhi to Raipur via Indigo flights. When you just see the status, they say en route. That means the flight from the Delhi to Raipur, that en route. So this is the en route. This is the en route. So again there is a possibility. H nu 1. Again there's also a possibility of different types of emission we can like H nu 3, and ultimately getting red. So just finally you are getting this. H nu 6, whatever it is fine. So it is a general plot that by, as I told you, my first initial part, that with the help of monitoring the fluorescence or emission or absorption of the products, one can directly monitor the transition state. So it is one of the very simple method by which we can probe the transition state. So let me summarize the whole thing first, that today we have discussed the probing of the transition state, and you must aware that there are many methods are available for probing of the transition state, and because in your course there is a femtosecond spectroscopy, or that is called the transition state spectroscopy. That is the latest method for the direct probing of the transition state. In addition to that, theoretically also with the help of ab initio calculation, one can also predict the transition state using very complicated quantum mechanical concept. But the initial method, which was proposed by the Polanyi and Brooks and other scientists, Satkamurthy, that is the simplest method. When there is no development of that femtosecond spectroscopy or resonance or infrared chemoluminescence method, they used very simple method, either by monitoring the D wings of the sodium line or sodium chloride, or you have seen the emission spectra of different types of product. They are able to detect the transition state. Thank you very much.